This video is about finding the average value of a function on the closed interval from a to b. I will state the mean value theorem for integrals without proof, and then we'll define the average value of a function on the interval from a to b. So here's the mean value theorem for integrals. It says that if f is continuous on the interval from a to b, then there is a number c in between x equals a and x equals b, such that the area under the curve, that's the definite integral from x equals a to x equals b of f of x, and I guess it's net area because this function's continuous and not necessarily positive, but that definite integral is equal to f of c times b minus a. So basically what this is saying is, if this, let's say the function's positive, like the one in this picture, if this represents the area under the curve, so this area here is given by that definite integral. What the mean value theorem for integrals is saying is that there is some x value in between x equals a and x equals b, where I can evaluate the function there, and that y value times that length b minus a, the area of that rectangle, is equal to the area under this curve. So they're saying there's some c out there so that this area, let's say it's this one, maybe that's the value of c. I evaluate my function there at c. This area, this red area here, the area of this rectangle is equal to that area under the curve. So we're saying there is a c value between a and b where that happens. Now, this y value here, f of c, we call that the average value of f on the interval from a to b. And I think it makes sense if you think about how we define average value whenever we have like a finite number of scores. Let's say you're trying to find your grade in this class. You've got a bunch of standards quiz grades. You add them together and you divide by the total number of quiz grades, right? That's going to give you the average. So if you had 10 quiz grades, you'd add them all together and then you'd divide by 10, and that would give you the average. Well, here we can't exactly do that because you have infinitely many points on this curve. So what we're doing instead is we're finding the area under the curve, and then we're dividing by that length. We're dividing by that width. So we'd say, what does the average height there have to be so that that length times width, or that length times that height, will still give me that same area. So that's how we're defining average. It's actually really easy to find the average value. All you have to do is evaluate the definite integral and then divide by the length of the interval. Finding the value of c, that's something different. Then you have to solve an equation, f of x equals this number, and you'll solve for the x value, which will give you c. I'm not so worried about c. I'm more interested in your ability to find the average value of the function. So let's do a couple of examples. This first question asks us to find the average value of this function on this interval. Just to visualize what's going on, I want to graph my function. I'm going to try to keep this to scale. So that's x equals 1. When x equals 1, y is equal to 1/2. Ooh, this is going to be hard to keep to scale, isn't it? And then when x equals 4, y is equal to 1/8. So if that's 1/2, half of that would be 1/4, and half of that would be 1/8. What's it's going to look like that? So when x equals 2, y is 1/4. When x equals 1/2, that's 2 times 1/2, that's 1, so y would equal 1. And so this is the general shape of this curve. I've got a curve that looks like this. And this is 1/2, and that is a y value of 1/8. Now, if I evaluate the integral from 1 to 4 of that function, it's going to give me the area under that curve. So that area is equal to the integral from 1 to 4 of 1 over 2x integrated with respect to x. So I want to factor out the constant, that's a 1/2, and then I have the integral from 1 to 4 of 1 over x dx. Now that requires now taking the antiderivative. By the fundamental theorem, the antiderivative of 1 over x is natural log of the absolute value of x. Then we substitute in 1 and 4 and subtract. So we get natural log of 4, or 1/2 natural log of 4, minus 1/2 natural log of 1. Natural log of 1 is 0. So we can just call this 1/2 natural log of 4. If you want, you could rewrite it. You could bring that 1/2 inside and make it a power. So that's the 4 to the 1/2 power is the square root of 4, or natural log of 2. So that's the area. And that's approximately 0.693. The average value of this function on this interval is that area divided by the length of the interval. That length of the interval is 4 minus 1. That's 3. So I'm dividing it by 3. So I get 1/3 times this, or 1/3 times natural log of 2 is the average value of the function. So we'll divide that answer by 3, and we get about 0.23. So if I drew a rectangle with a height of about 0.23, the area of that rectangle is going to be exactly the same as the area under the curve. That's a little bit hard to see because the numbers are so small, but that's the idea behind average value. Okay, now we've got an application problem involving average value. It says the volume in liters of air in the lungs during a 5-second respiratory cycle is approximated by this mathematical model. So volume is 0.1729 times t plus this constant times t squared plus or minus this constant times t cubed, where t is time in seconds. Then we're asked to approximate the average volume. So as soon as I see average volume, I need to use my average formula, my average value of my volume function in the lungs during 1 cycle. So I need to think, what is 1 cycle? From t equals what to t equals what? Well, they told us that we have a 5-second respiratory cycle, and t is time in seconds. So that tells me I should be integrating this function from 0 to 5. That's 1 cycle. So the average value of v is the integral from 0 to 5 of v of t. With respect to t, we're using t instead of x. And then we divide by the length of the interval. That's just 5 minus 0. So dividing by 5 is the same as multiplying by 1/5. So we'll get 1/5 times the integral from 0 to 5 of v of t. So I will write that down. I've used my average value formula. I've simplified it. And now I want to substitute in my v of t. Volume is a function of time. It's right there. So we bring the constant down. We add 1 to the exponent and divide by the new exponent. And then we bring the constant down, add 1 to the exponent and divide by the new exponent. And bring the constant down, add 1 to the exponent and divide by the new exponent. That's the anti-differentiation step. So we start by writing down our average value formula. Then we evaluate the integral. First we anti-differentiate. We substitute in 0 and 5 and subtract. So this is our f of b minus f of a step. So we want f of 5 minus f of 0. At t equals 5, we get this. And when t equals 0, that's 0 plus 0 minus 0, so we just get 0, and we subtract. So that's it. That's our answer. Okay, so now let's simplify this. I would use a calculator for the arithmetic myself. So I'll do this. Actually, let's divide everything by 5. So one of those 5s will reduce in every exponent there. So that was a 5 squared, now it's just a 5. That's 5 cubed became a 5 squared, and that 5 to the 4th became a 5 to the 3rd. And now we get this answer, 0.1729 divided by 2 times 5 plus 0.1522 times 5 squared, that's 25, all divided by 3. So that's that, minus 0.0374 times 5 cubed, all divided by 4, and we get that. So that is approximately 0.5318. If you're saying 0.5318 what? Well, let's look at this. This is the volume in liters of air in the lungs during a 5-second respiratory cycle. So on average, we have about 5.318 liters of air in our lungs and every 5 seconds. That's the average value of the volume of air in the lungs. Okay, so how do we do average value? You just integrate the function over the interval and you divide by the length of the interval. That's just b minus a. Super simple, but it has some very interesting interpretations, and it's a great opportunity to practice the fundamental theorem of calculus.